Good day to you. This is Galactic on a Sunday here in Chico, the 11th day of May. And over here you'll see, as it says in the caption, Harvard scientist beautifully explains quantum entanglement and non-locality. Now we're going to listen to a brief clip from this, beginning at the 8-minute mark. The video runs to about 12 minutes. There's some information at the end that Jaimungal is required to include if he wants to get any money, which he does. He's making a living. So's the Harvard scientist, and the Harvard scientist is getting paid, as is Jaimungal. That's the only background information we need. This could be completely innocuous, or it could be just another wild goose chase. I'm going to show you that this is where we need to begin, as laymen, to understand quantum mechanics, a topic which has not been understood for a century. The greatest minds in the history of mankind have been unable to penetrate this paradox to any degree whatsoever, indicating directly that there's a fundamental problem in mathematics. And you'll hear that this Harvard scientist beautifully explains not quantum entanglement and non-locality, although those are his topics. What he's going to beautifully explain is that mathematics is destroying science. And Bohm wrote a whole book on how mathematics is destroying science, and Paul Dirac wrote a book on how quantum mechanics has destroyed science. So it's not quantum mechanics that's destroyed science. Quantum mechanics is the indicant of absolute failure. And nobody's able to go back far enough to discover what went wrong, because we know that science works if it's done correctly. It's not being done correctly. But you have all of these magnificent minds, including Einstein, Dirac, and Bell, who are just simply incapable of penetrating the mystery of how science has halted. Although it's worked to discover electricity, it's worked to discover telescopy and microscopy. It's worked to discover how to harness the energy, the power, the forces of nature, and yet we cannot obtain the fundamental relations in the universe that describe it. It's obvious that some mistake was made in general relativity, but it does have local significance for spaceflight, and indeed for GPR. If I'm saying that right, geopositional measurements using satellites, which require general relativity in their computations. So it does work. It works linearly. And I've discovered there's a major flaw, not in Einstein's formulation, which is correct, it works, but it works with the calculus, and therefore there is a flaw, because you can't use the calculus, and I proved that. So we're getting into some really deep stuff. And you don't need to concentrate right now on what I just said, which is admittedly quite provocative. But I've made a fundamental insight that does, obviously, to me, indicate the right direction in which to look. And that's the purpose of a theory, is to indicate the direction of future research. This can be abused, because if you're going off on a wild goose chase, such as for the cosmological expansion theories or theorems, then you'll never get the right answer because you began with the wrong premises. Now, on that note, we're going to listen to this Harvard scientist who I think is an excellent speaker. He's obviously worthy of his post, and I do judge men this way. Not as men, but as proponents of science. This man does a good job, and I hope you enjoy this. This will be less than 4 minutes, but I will punctuate what he's saying with some explanatory comments. You did not hear the first 8 minutes of this, but I can assure you, first of all, I recommend that you do listen to the whole thing all the way through. It's about 12 minutes, which is not much. It's excerpted from an earlier, more extensive interview with this Harvard professor, who's going to beautifully explain quantum entanglement, and I'll show you that he does a beautiful job not of explaining it, because it can't be explained, not with linear mathematics, but it can be explained with the correct mathematics. That's what I discovered, which is Again, quite a provocative statement. So I'm the one who should be being interviewed. I'm just saying that to get it off my chest. It's a form of sour grapes. It's a form of aggrandizement of attention. But in science, that's what you have to do. If everyone around you is wrong and you're right, you have to speak up. I'm doing so. Just yesterday, I produced my first live stream video. I've made over 960 videos in under 3 years. I'm well on my way to solving all the equations, including Dirac's, Schrodinger's, Heisenberg's, Einstein's, and ultimately Planck's, to get the quantum solution that we need to understand universal physics. All right, that's a tall order. It's been a tall order for a century. It's about time we got it. I believe in science. I know that it works. So something is fundamentally wrong with the scientists. They're not bright enough to see what the problem is.
So in other words, Bell is trying to close a possible way out of the non-local causation. EPR says there's either non-local causation or hidden variables, and Bell is saying, well, even with hidden variables, you still get non-local causation. Therefore, quantum theory is simply a non-local theory, and that's the end of the story.
All right, that's the end of the story. You heard him mention John S. Bell, one of the most famous names in the history of quantum mechanics, because it reopened scientific inquiry to what's going wrong with the mechanical system. I want to explain what is meant by non-locality, because it is the key, and everyone agrees on this, that it's non-locality. There is a complicating factor in saying that, though, as with anything else in quantum mechanics. What does it mean, non-locality? It means spooky action at a distance. Non-locality is a term that was invented to distinguish two sides of a certain coin, which is quite problematical and paradoxical, which is that you have the general theory of relativity, which has virtually proved that superluminal information transmission is impossible in the universe for the simple reason that nothing at all can travel faster than light. So that's an upper speed limit as it was composed by Einstein in the general relativistic formulation, which has a context. It is called a gravitational theory, but that actually doesn't say enough. Gravity itself is spooky action at a distance, which Newton had to deal with and everyone's had to deal with ever since. What Einstein discovered is that space has a characteristic, and that's something brand new in science that's changed science forever. To concentrate on that involves certain, I'll just say equations, but it's better to call them relationships. An equation is a relationship of equality, but there are other kinds of relationship, such as the conjugal relationship, with which you might be familiar, and if you're not, don't worry, because we'll be getting into that shortly. Conjugality has to do with orthogonality. All right, so I hope that doesn't lead your mind astray. It's rather difficult to corral this problem. We're focusing now on non-locality, which, as I have just explained, is spooky action at a distance. And let's be more specific. What you'll hear being discussed here is the phenomenon of entanglement. And entanglement means that two particles are coordinated. These are usually electrons, but they can also be photons. And when they're coordinated, they're brought into proximity and set to a state that binds them together. And that can be seen, it can be observed in experimentation, what happens after that. It shouldn't be called entanglement, it should be called coordination, because the two particles can have states, and as you know, these states are fairly well defined. But in the case of entanglement, you're setting the two particles such that they share a property. And now the conundrum, the paradox, the baffling situation that leads to the concept of non-locality is that if you now separate these two particles, you believe that you're separating them. That can be measured by distance, but The experiment that needs to be done to show non-locality is excruciatingly difficult to measure. It's difficult to set up, it's difficult to execute, and it's difficult to get the results. And you'll see that this will lead, as it inevitably does these days, into the Alice and Bob situation, which I consider to be absurd. There should be no talk of Alice and Bob. However, the way that this professor, and indeed all of quantum physicists, have approached this statistically, is that when you separate the two particles, that they now have a space-time separation. What I will be showing you toward the end of this brief presentation is that you're not separating the particles in space-time, because you've bound them, you've coordinated the two particles with a spatial characteristic that they're very close. You can't coordinate these two particles except when they're extremely close, because it's really a magnetic property that you're attaching to the two particles. And magnetism is an interesting phenomenon. Of course, it's related to electroforce and magnetoforce conjugal characteristics. They are known to be right angle phenomena. James Clerk Maxwell proved that. They're not polaric, they're orthogonal. That's in all the textbooks, but you don't hear it said that way, that they're orthogonal, but they are. And that's paradoxical. That actually will end up being the quantum paradox, and one of the approaches to the direct solution by which there is no more paradox anywhere, not even in entanglement. I have that solution. Nobody else does. It's virtually impossible to see the solution because it requires an induction that requires a stepladder sequence of paradoxical solutions, which have to be tiered in the right way so that you can wrap it up with a proof. And that's what this man is going to be talking about. Let's listen further.
That's what he did. This theorem has gone through a giant game of telephone. People have. So first of all, I should say that the paper was like published in an. Bell was not. He was a particle physicist doing this foundational work on the side, and he would caution people against doing foundational work because it was considered very bad for your career, which is really shameful. Physics is supposed to be an intellectual enterprise. And closing down avenues of intellectual investigation, of exploration, is just anti-intellectual. That's a shame. But his paper somehow eventually became more widely known. And it's like through a game of telephone. And eventually people began thinking that what he did was prove there couldn't be hidden variables. And so people would say, oh, you have a hidden variables theory? That's ruled out. Bell said there can't be hidden variables. In fact, the Nobel Prize was given for experimental tests of the violation of the Bell inequality, right? There's this Nobel Prize that was given to Clauser and Zeilinger and was it Aspey? I think it was Aspey also.
Right.
Yeah.
That's misspelled.
And it says, if you look at the press release for the Nobel Prize, it says that Bell proved there couldn't be hidden variables, and this Nobel Prize is given because they proved hidden variables are impossible. That's
all right.
Bell showed it all. In fact, not only...
Not what Bell showed at all. All right, you've heard of hidden variables. Einstein, in his paper with Podolsky and Rosen, challenged the quantum mechanical system itself by stating that due to the experiments being conducted to show basically the paradox, the entanglement, that is impossible because of general relativity, which predicts that there cannot be non-local action. This concept of action at a distance has baffled men since the beginning of time. We can't explain gravity, we can't explain magnetism. There are several phenomena associated with those two that simply can't be explained using a conventional linear approach because they have to do with fields in space. What Einstein was able to show with general relativity is that space is curved, and that is correct. Space is curved, but you must not say anything else. Space-time is not curved. although it might be. I'm just saying what he showed is that you can state that space is curved. And if you say that, you can explain gravity. And he proved that that can be done with a linear solution, which cannot be complete. And I'll show you why. But this leads to the basic paradox underlying all the others. It is non-locality, which you must define precisely. What Einstein said in the EPR paper is that non-locality violates light speed. Does it? Does non-locality violate light speed? To determine that, you would have to precisely define what is locality and non-locality. Look at the two particles next to each other where they're coordinated with an electromagnetic field. Actually, a magnetic field is applied. That's one way to do it. And now the two particles are associated. But what is very difficult to see is that they're not associated entirely in space itself. If they were, then when you separate the two particles, there should be a time lag because of the distance. That is general relativity. With every distance, there is a coordinated factor called time lag, and entanglement violates time lag. In other words, it violates light speed because something can be shown to happen. When you separate the particles, they don't know that they're separated. And that violates what we see. So there's something unseen going on. That is the key to the paradox. What is it that is not being seen? Well, whatever it is, it violates time. It doesn't violate space unless you say so, and Einstein said so. That violates the space-time relation, but he's saying that there's something going on that's violating one or the other. And they're combined, though. He proved that space has a time component the way we measure it. Are we measuring space correctly? We have to assume that we are, because we know that distance is, although Einstein said there's another factor, well, right there you have to stop. That's what changed. That space is not just space. It's something else, combined. This is very similar to the electromagnetic relationship, which is orthogonal. Now, he said that time and space are orthogonal. What I discovered is that space is being composed incorrectly in 3D, and 3D is what is used in space-time, 3D. We've heard it said that it's 4D. I'm sorry, but no, it's not. It's 3D, because that's the space component. So it's embedded. And all Einstein did was add a fourth imaginary axis. That's an axis that we can't see. So Einstein actually got the answer, but he got it in linear space. That makes a 3-1 split. That's called the Einstein signature. You take 3D and you add a fourth imaginary polarically negated axis, where the three axes of space are going out. You could say that. But if you do say that, then the fourth axis is going in. That bends the space. That bends the space. And then you need calculus and complexity to deconvolve what you just discovered. But what you're going to discover when you use mathematics to obtain the curvature from the hypercubic system, which is not curved at all, it's linear, it's hyperlinear, you're missing out on the imaginary component. You're conjugating on the 3-1 split. That's not a match. You're missing something. And I want to show you very carefully how you can solve that. Watch carefully. This is 3D space. We're going to drop this, and make it not 2D but 2 something. And now we're going to add to time another component, and now it's a 2-2 split. You need a different mathematical basis to use that. But when you do, you can perfectly see the coordination between the two particles, which when you separate them, you're indeed separating them in space, but you're not separating them in time. And we'll be back with more. That's 21 minutes. Thank you for tuning in. I'm sorry that my voice seems to go up by itself, and I know why, and that's a red flag. I can't control it fully because I'm highly emotionally charged right now. I'm ready now to be a scientist and express the ideas that I know, and I've attempted to do so here. Thank you again for tuning in. Keep looking up. We'll be right back later today with more.